All right, hello everybody. Welcome to day number nine, like this, of 66 days of data daily live stream challenge. And I must admit, I'm running out of fingers, so I need to make up my mind how I'm going to show you the days after tomorrow. But that's a different story. So today we will cover once again mathematics. So we started with descriptive statistics, which I would say is a part of mathematics. Yesterday we talked about things like median and mode and mean, which are quite important in today's video as well. That's why we took them first. We also talked about variance, standard deviation, range, and quantiles. And today we're going only to talk about two measures, so to say, and those are skewness and kurtosis. And I hope I'm spelling that right. I'm a finance person, not a mathematic guy, but so that's just the way it is. And we're going to use a lot of yesterday's stuff in today's discoveries as well. So as always, I have linked the KNIME blog page for the 66 days of data challenge in the video description down below, and we are going to switch over to the screen right now. Okay, let me do that. Here we are. So we are in category or week or whatever, number 2 in day 9, and we're going to learn today about more complex statistic measures, skewness and kurtosis. So please let me know in the comments down below. Is it called skewness? Skewness. I know there's a term of skewed, but so I assume it's skewness and kurtosis. I hope that's right. All right. So what are these two? And I basically looked at this very last link that the good guys at KNIME here provide: shape of data, skewness and kurtosis, because I guess that explains it very well. So shape of data, skewness and kurtosis. So these two measures, they basically talk about the symmetry of the distribution of values that we have. If you remember, yesterday we looked sometimes at singular values. For example, we looked at the median, which is the value that is exactly in the middle of a data set, right? And we're going to come back to this one today as well. But skewness and kurtosis basically are talking about the shape, and that relates to that median. If you imagine, I guess that's a good picture. If you would imagine median as a kind of axis around which things sometimes evolve, that would be maybe a good approach. Important here, it's not the middle axis, which we will discover in a second. So skewness. Skewness is basically a degree of asymmetry observed in a probability distribution that derivates from the symmetrical normal distribution. So if we look up normal distribution in Google Images, this is a normal distribution, right? If we just go to images here, we see this is a standard normal distribution. This bell-shaped curve is also something that you hear quite a lot, and you see this in all kinds of things when you're talking about people adopting technologies. So early adopters, late adopters, and so on and so forth, the big group and all this kind of thing. That's normal distribution. Skewness is a degree that basically says if things are not so evenly distributed than we have just seen today. In basically when we have the normal distribution and it's completely symmetrical, median, mean, and mode, the three values that we talked about yesterday, are basically the same, and they are zero basically. So that means that that the median is exactly in the middle, and the share on each side of that median, if you look at that chart, is basically equally shared or of equal size. But skewness is a different, it's a kind of different thing. So what types of skewness do we have? So we have, for example, positive or right skewed data sets. So if you look, the number of students here and the results that they have is that a very low number of students having high scores. So that is a right skewed data set. So the median, and I don't want to use that all the time because I know the data scientists are going to kill me for that. The average is here, and the more we get to the right, the more we get to the better results, the more flat the curve or the tail becomes, if you want. So that's basically right scoot. So that is mean is bigger than median, bigger in regards to the number, the result, the number that we're looking at. So mean is bigger than median is bigger than mode. Then we have a right scoot data set. On the other hand, we have a negative scoot or left scoot data set. And that is exactly the other way around. When we have like a front tail, if you want, or if we take the other one and just mirror it, we basically have mode is bigger than median is bigger than mean, right? That could be an adoption curve or something. Like not very much people adopt a certain technology early on, but then the big mass or the big group of people comes. So here is basically, and therefore it's important that we also consider yesterday's lesson. And if you have not seen that, I link it up in the video here at the top somewhere. So if you want to talk about calculating skewness, you have basically several methods, so to say. So for the first coefficient, you subtract mode from mean and divide that result through standard deviation. The thing is helping if the data present has a high mode. But if the data has low mode or various modes, which we have also discussed yesterday, this coefficient calculation is not preferred, and we should have a look at the second one. So the second one goes like this: multiply the difference by 3 and divide the product by standard deviation. And then if the skewness is between minus 0.5 and positive 0.5, the data is nearly symmetrical. If the skewness is between minus 1 and minus 0.5, then it's negative skewed, or between 0.5 and positive 1, it is positive skewed, and the data are slightly skewed. If the skewness is lower than minus 1 or greater than 1, the data is extremely skewed. So what does that tell you about your data set? Maybe that's the question you have in mind. Basically, it gives you an insight about how evenly shared your data is. And if we consider this here, this positively skewed data set, where a few people with very good grades are outliers, you don't want to make them the standard. You don't want to apply calculations and say, hey, this is the standard. So in further steps down the road, we have to make sure that we have representative measures that we're talking about our data set, right? These people that have extremely high grades, they are not representative of the group of all students, so to say. That's where skewness is important. So let's have a look at the second. That's at least my understanding. So if you know it better, leave a comment down below. As I said, I'm not a mathematician, and I'm happy to learn how to phrase it better. So let's have a look at kurtosis. Kurtosis refers to the degree of presence of outliers in the distribution. So basically, if you see the middle curve here, that's the normal distribution, right? If you have a positive kurtosis, you have a very high shape, whereas in a negative kurtosis, you have a flattened shape. And the words for that, for positive, are leptokurtic, negative are platykurty, and normal distribution seems to be mesokurtic. So I hope I'm pronouncing this the right way, guys. In finance, let's just read in finance, kurtosis is used as a measure of financial risk, and a large kurtosis is associated with a high level of risk for an investment because it indicates that there are high probabilities of extremely large and extremely small returns. So as always, if there is a high chance of winning, you usually have a higher risk. On the other hand, A small kurtosis signals a moderate level of risk because the probabilities of extreme returns are relatively low. So, the excess kurtosis is used in statistics and probability theory to compare the kurtosis coefficient with that normal distribution. So, once again, we're always coming back to the normal distribution. So, types of excess kurtosis, we had it already. Leptokurtic or heavy-tailed distribution, kurtosis more than normal distribution. Mesokurtic, kurtosis is the same than the normal distribution. Or platykurtic or short-tailed distribution, kurtosis is less than the normal distribution. So let's have a look at each of them. Leptokurtic, that's this one. Once again, that's when we have the chance of high rewards, but also high risk. And platykurtic, basically low risk, but also the chance of low to no returns. So tomorrow we are going to look once again into KNIME, and we're going to look to bring all these numbers into meaning when we look at tomorrow's task, day number 10, because we will use a fantastic notes that gives us some descriptive statistics about our dataset. So if you think that is interesting, I'm happy to welcome you tomorrow on that session, and I'm really looking forward to see you tomorrow. And yeah, have a great day, have a great evening wherever you are. See you for tomorrow for day number 10 of 66 days of data with KNIME. See you tomorrow.